Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're gonna talk about space elevator. So let's dive right into it. Now first thing you have to understand, the idea is very simple. It allows you to go from a surface to orbit very easily or to space very easily. So it's generally either thought of for planets, let's say Earth, Mars, Venus, or for moons like Titan, Europa or Moon. So that's the whole idea. It simply allows you to go from planet surface to space. Now, to simplify the concept even further, just think of it as an elevator. That's why it's called space elevator. It's nothing magical. It's simply a cabin or basically cab where you get into it and you get off in space. That's all there is to it. Basically, very, very, very tall orbit. So we can think of many things. Now, question is, does physics allow it or not? Because if physics says no, you shall not pass, you will not pass. That's it. So whenever we talk about space elevator, here's the deal. The physics says it can be done. Physics is very clear on that. If you can build the material, physics is saying, okay, go ahead. So what do we need for that? Now first, cable, whenever we are talking about elevator, think of it as more as a ropeway, only going vertically. So you will have from equator to geostationary orbit. Now what about that cable? There is no pillars in between to, pillar or post to hold it steady. So how it's gonna be like, exactly where it's supposed to be. It will be under tension. Basically it's like you're pulling it. It's like a span bridge. So how do you pull it? Like it's in space. So how you are pulling on it? Very simple thing. You will put a counterweight on geostationary orbit. Now many of you will be like wondering why geostationary orbit? If space starts at 100 kilometers, why not just put it something there? Problem with that is that if you want to orbit at basically low Earth orbit, you have to travel very fast, like very, very, very fast. Now how fast that is, basically you will be orbiting for every 20 to 30 minutes. That's not suitable. Like the lower end of that will be also moving that fast, so it's flat out of the question. Geostationary on the other hand is a very perfect orbit where you have the speed that is matched with the surface of the Earth. So basically if you are looking down from geostationary, you will see a patch of Earth that is exactly not moving. So you will, even the rotation of Earth from your vantage point will look, it's not rotating because you will be rotating with it. So this allows you to put a counterweight that from that point, let's say you have whatever you have it, a giant space station, an asteroid, whatever, because it has to be heavy. Whatever you have here, from that point, if you look down to Earth, you will be like, okay, Earth is there. It's not moving, it's not spinning, it's not. So that way you can put a cable down. Now be mindful, even though most of our satellite is below geostationary orbit, you can't use this system for low Earth orbit. Now you're like, whoa, we are going so far up, why can't we just stop the elevator at low Earth orbit and ta-da. Basically think of it this way. If you haven't seen rocket launch, you would be familiar with the idea that rockets always go up and then they tip over. Now that tipping over is there for lateral velocity. It needs velocity. It does not need height, it needs velocity. That's why we always classify it orbital velocity. We never say orbital height. There is no orbital height. No matter how far you up, if you're not traveling at the right speed, you will fall back. So to gain that speed, height is no matter. Now, would that help us in low Earth orbit? Yes, it will help, simply because we will remove the lower stage of a rocket and simply launch from higher up. So even though you are falling, you can use that velocity, you can use that falling velocity as a gravitational assist, and then you can just circularize the orbit. You will still need rockets. For low Earth orbit, you will still need rocket, but rocket cost will go from few $1 million to few $1,000. So it's still useful, but be aware, like if you can't, if you're like, okay, in emergency, let's say stop at Leo and you just gonna go out and float in, you're gonna fall. Now it will be very cool as Red Bull jumping, but let's just say other than that, nothing else will happen. So you have to get off at geostationary orbit, because at that point you are at orbital velocity. Before it, you are not at orbital velocity, you're just gonna fall. So, and be aware, the counterweight will be higher up than geostationary. Now, like why? Basically, because if you're pulling tension on something, you want a center of mass, basically center of gravity or center of mass, to be at exactly geostationary. Now, if you are familiar with anything that moves, anything that has geometry into it, it's never as simple as that. Okay, exact 50%, exact 60%. It may, it's more of a combination of mass and other properties. So you want that center of gravity or center of mass to be at geostationary. So you have to pull it up. The counterweight will be always up because it's under tension. Now the cable, even though it's very long, it's not going to be heavy because the counterweight is balancing it out. So for that reason, this point, basically wherever you have that geostationary orbit, you will have a get off point. You could have that, or you have to go a bit up, or like more to a graveyard orbit. So that's the physics. Physics is like, okay, go if you can build it. Now, when we are talking about Earth, we have to understand that geostationary orbit from Earth is at 36,000 kilometers. Now that 36,000 kilometers is just that, 36,000 kilometers. How far that is? To give you a context of it, think of it that way. Earth's diameter is smaller than that. Just think of it that way. Your Earth diameter multiple times is the length we need. It's a very, very long structure. Even on a basically planet scale, it will be longer than the planet. So it's a very, very tall structure. Now it will only allow from, if you want one tether, it will only allow you from equator to geostationary. Now you can go, put it, let's say, in USA. Now problem would be that you have to put something counter to it on the other end of the globe. Basically, if you're going, let's say this is your equator, you're going to USA, you have to put something else at the other end. That way you can have two from poles also. So, but then again, if you can only afford one, you have to put it in orbit, basically equator. Now, as we talk about this, now you might be like, okay, if science is allowing it, if mathematics is clear, then why don't we do it? Simply, there is no material strong enough. Whenever you read articles about space elevator, this and that and all that, everybody will say about carbon nanotubes, magic material. Now, when you're talking about 36,000 kilometers, now be mindful, even if it's 1 gram per meter, something as light as that, 1 gram per meter, how many tons it will become at 36,000 kilometers. So you have to understand, most things will break under their own weight if you stretch them to 100 kilometers, let alone 36,000 kilometers. So carbon nanotube has what we call tensile strength of gigapascal. Basically, you have to pull it very hard to break it. Now, whenever we build something, we generally overbuild it. You never want to your cable for your elevator to be like, okay, if minor scratch happen, boom, your cable fails. You always want enough redundancy. This, on the other hand, mathematically is barely good enough. This part I have rarely seen addressed, but this is barely good enough. So whenever you are talking about this, even though let's say some magically you can figure out how to make this, which we haven't, we have only made micrometers of it. Basically, it's not even a long strand, let alone a strand that is as long as 36,000 kilometers. And every time you have a gap in it, it's structurally weak there. So it has to be a continuous strand. So flat out we haven't made it, and minor scratch, let's say even a minor debris hit it, it's gone. And you can't make it very thick because, well, again, I told you, it's almost at the breaking point anyway. So there is no material. Now let's say we figured out something to enhance its strength, or like have tri-carbon nanotube, where you will see one nanotube inside another nanotube inside another nanotube, and let's say you can get the tensile strength to be even higher. What about that? Now the climber, you are talking about 36,000 kilometers. To climb that distance, you need a lot of power. Now you might be like, okay, we'll have solar panels once we go up. Yes and no. Be mindful, you are not at orbital speed. So basically you are not in a place where even a minor thrust will do. You are not weightless. Be aware of that. You are not weightless. You are fighting against full gravity of Earth, full of it. And at the altitude of basically ISS, you are still at 88% of the Earth's gravity. So the climber, whatever the pod we have, it has to fight against gravity. It's basically climbing itself up, and it's not doing in 0G. It's like it's not like that. It's like it's like spending a lot of energy to do that. So we need a lot of power, like a lot of power. Of course, as it goes up, it becomes easier, but during that early stage, let's say 1,000 kilometers, it needs a lot of power. How much power? In megawatts. Now you might be like, okay, we have the cable, might not just use that. Again, this is the weak link. It's not strong enough to have, like, power cable also. So, and if we did that, even then you will need giant power station on both ends to make sure that it works. So power requirement is kind of overlooked, because this equation will be like a giant nuclear power plant that is supplying enough power just to get it up. Now whenever you're talking about low Earth orbit, basically where the interesting thing is, and people want to be at low Earth orbit simply because you are protected by a very thin atmosphere. So it's not that there is at zero atmosphere, it is very, very, very thin atmosphere that does protect against very fast meteorites, and you are inside the magnetoshield. Basically the radiation here is kind of low. You go above that, radiation is going to be roasting you. So let's say for some reason you want to have your space hotel in low Earth orbit, best place to be, you can't use this elevator for that, because if you get off the climber at that height, you have to have boosters that is going to give you the orbital velocity, because you have the orbital height but you don't have the orbital velocity. So You can understand. So if you want to go from Earth's surface to low Earth orbit, normal rocket is better. This is case for Earth. Now, even though this sounds hopeless, it's not as hopeless when we talk about moon. So let's say I have already made videos about moon mining. You can check it out here. Now, whenever we are talking about moon, you have to understand it has very low gravity of its own. Very low, very low. You can be like Superman there. Now, but it does come with a consequence, because moon is geostationary, like tidally locked to Earth. That's why you only see one face of it. It does not have what we classify as geostationary orbit. There is no orbit where you can spin and you will be like geostationary to the moon. However, it does have one thing what we classify as Earth Moon Lagrange point, basically where these two body cancel the gravity out. That place will be our saving grace, where we will put our counterweight. However, the cable length we are talking about here is 56,000 kilometers. People are like, whoa, that's longer than that. Here's the deal. It will not be under same stress as Earth system, because gravity is basically many times lighter. So that's the good part. And as of now, as I talk to you, Kevlar and other materials is strong enough to do this. With today's technology, we got it. We can do it. Let's say if we really start to do moon mining, and we are instead of using maglev system, and let's say we want to build something like this, moon elevator, we can do it. In this case also, you will have basically the counterweight away from Lagrange point, because you want your center of mass, not the actual mass in the center point, but center of mass to be at that point. So this will be very doable situation, even though it's 56,000 kilometers, because you are going away from very low gravity and enough solar power. You can do it with current technology. If we want to, we can start building it today and it will be finished in 10 to 15 years. We can do this. Now, okay, if we can do this on moon, what about doing it for Mars? Now, Mars has one good thing. It has lower stationary orbit. Basically, if you are talking about geostationary orbit, the reason why we can't call it geostationary in case of Mars is because geo means Earth. Geocentric. Geo means Earth. That's why I'm calling it stationary orbit. It's at 17,000 kilometers. Now, you might be like, okay, that's very close. That's if we can do with Kevlar on moon, can we do it here? Yes, because it also has lower gravity. However, not as low as moon. It's many times higher than moon. So what about the counter? Now this is where we are very lucky that there is a counterweight, basically one of the moon, Phobos. It's a very small moon. Do not think it's a moon big enough that you can even see with blind eyes. I'm saying with your unaided eye. You have to know where exactly you're looking. It's a very small point. It's not like our big moon where you can easily see it. This is very small. So we can move it and we can build it. However, because of the gravity, it's not as easy at moon. Like moon, if engineers got together, scientists got together and funding got together, we can do it in like 10 to 15 years. Here we are pushing it where we have to be above Kevlar. Basically, there are some materials, but they don't last very long. There are materials that can handle more than that, but they don't last long enough. So, but in case of moon, we got it. In case of Mars, we can get it. I'm optimistic about it. However, in case of Earth, there is no scenario here, like flat Earth, just no. So this was my presentation on space elevator. I hope you liked it or learned from it. And in that case, please leave a like. If you didn't, don't worry about it. You can dislike it. I would urge you to leave a comment on my video. I reply to all of them. And subscribe. Press the bell icon if you're free. And as always, thanks for watching.